So this is Shelby Fleischer. Um, I was asked to talk about crop pests, and as I tried to envision what I would talk about, it kind of narrowed down to three things, talking about rain shifts. There's a lot to talk about. A lot of people are already talking about that. Phenology and volcanism and how those interact, and some migration discussions. Okay, so, and I've been working, I'm retired recently, working a lot in Pennsylvania for the last 30 years, more used to speaking in barns and uh, bars and things in extension systems, and working in Pennsylvania, which crosses all these different physiographic provinces. And one of the questions that is rain shifts. So during the time, the 30 years I've been working, I've seen lots of species arriving earlier over wider areas that are relatively new to Pennsylvania. We've talked about that a lot. So we're seeing rain shifts in space. Back in 2008, the Union for Concerned Scientists tried to put together a document for the Pennsylvania legislature. They were lobbying for a particular program. They asked me to get involved with this, and they asked me, like, what insects will start showing up that haven't been shown up before. And so I made a list of all the insects that I have to write pesticide recommendations for, and I highlighted the ones that were probably going to be a problem. And you don't need to look at all of this, you just need to see that, and this is organized somewhat by crops. There's a lot of yellow here. So yes, we're going to get a lot of rain shifts in space. That's not too surprising. And that's going to be happening. I want to point out there's other kinds of rain shifts. When we deal with certain groups of insects, we expect them to be hotspots that occur when temperatures are high, typically because they outrun their natural enemies when we have background conservation biocontrol. So hotspots occur when temperatures get high. I'm expecting more spider mites, more aphids, more whiteflies. So we've got these rain shifts in temperature space, so to speak. And then conservation biocontrol. It's a critical part of what's going on in our ag systems, if it's unless it's protected ag, and then we, in greenhouses and so forth, that's where you get a lot more people buying biocontrols and putting them in there because they're not there naturally. And I've just shown some of them up there. And my question is, what's going to happen with this tops-down biocontrol? There's a lot of research. I just pointed to one summary thing that was recently out there with some 68 authors, scientists warming on climate change and insects, and they're talking, this is coming from that literature that's all worried about, it's not in the ag literature, they're in the conservation biology literature, worrying about dramatic declines in insect populations. And so we might see some of that, and I kind of read through that, and there was very few examples that dealt with ag production systems. But of the ones that did, they did talk about that, higher trophic levels, maybe a stronger influence on specialist species relative to generalist species. So we need to consider rain shifts at that, and I don't think we have data on that. Okay, so rain shifts, we have species that overwinter poorly, say rain shifts in geographic space. Pests that outrun their natural enemies, their development rates are higher than their biocontrol natural enemy rates of development, and possibly rain shifts of natural enemies. Okay, phenology and volcanism, how they interact was something that I was very interested in, had some students that worked on it. So insects develop faster at optimum temperatures. No surprise, this is your classic developmental rate curve. And you can see that the development for this insect from egg to adult, can be cut in half by, between 70 or 86 degrees Fahrenheit. So this can happen pretty quickly. But diapause pauses development. So this whole idea that we can use degree day models to model things all assume that we're working with those life stages that are responding to temperature. But insects, overwinter, or they estivate in very hot temperatures, so they have the ability to diapause. And it can be, and this is just showing for great berry moth, prior to this particular day, none of them will be in diapause. After this day, all of them will be in diapause. In this particular case, the diapause cue is sensed by the egg. So we've got a great berry moth that's laying its egg. That egg is sensing the cue that egg will continue to develop all the way to a pupae, but whether that pupae will go into diapause or not depends on which side of the photoperiod they're on. So how do these two things interact to influence voltages, or number of generations per year? And so I'm showing you a diagram of a individual-based model or agent-based model that we ran. And I don't want you to get bogged down by the weeds. I just want you to note that we're taking like 1,000 individuals, running it multiple times, and you put them in as diapausing pupae, because that's how they overwinter. And then we have diapause termination models, we get first generation, degree dated models, you get a second generation. Those eggs will, they might diapause. And in this case, out of 1,000, we now have that one counted. Or it might try and develop into a new generation. And if it tries to develop in a new generation, if there's enough degree days, it'll pull it off. If not, it'll die. So what happens when you look at these processes together? The top panel here is showing the simulated data versus the observed data from malaise traps, and kind of a way of trapping adults. And we were able to model it reasonably well. And then we compared that to a low emission scenario and a high emission scenario. And this work was done, gosh, 2010. We're dealing with global circulation models that are considered outdated, but we got the data for the temperature profiles from Catherine Hayhoe that gave us downscaled simulation data of the day. So you can see the populations, the generations shifting forward in time. And so you got generation 1, 2, 3, 4. So one thing is they shift forward in time. This shows you the emergent state for each generation, and the emergent state is occurring earlier. So the lines are shifting, they're declining. And interestingly, you can start seeing in this graph the magenta triangles at the top is a relatively small fraction of those 1,000 individuals that we simulated. That's a fifth generation, which has never been heard of for this insect in this location. What we saw overall is that when temperature and photoperiod interact to influence, in this case, great berry moth development and volcanism, generation 1 starts earlier. No surprise. Each generation develops faster because the temperature is warming. The time between generations compress. And that becomes critically important because now we have overlap among generations. And with insect populations, they're stage structured in our IPM programs. If you've got clean stage structured things, you can start saying, well, time your management for the egg hatch and neonate larvae, get your management done before they get into third instar. And you can start using relatively selective management options or insecticides. But as you get overlap of life stages, it gets harder and harder, and you start relying more and more on biocides. So, we're getting greater overlap among generations, and that's another result of this interaction that isn't always appreciated. In this case, we got a potential of an additional fifth generation by the end of the century. Not simulation. Okay, so temperature so we use the last examples I told you about. That was under climate change scenarios with mean temperatures following what those simulations were from Catherine Hayhoe. But daily temperature range, the difference between high and low, is also changing. I think effort work. You pointed that out in your work as well. So what happens when we just get change, you can have the daytime high increase and the nighttime low decrease or increase. What's the interaction when those things happen? So we also looked at that. This is not moving forward in time. This is just based on the average temperature that was happening around 2010. So it's what, 15 years ago. This gives you a picture of a given day in Stewart, Virginia, day 100, so we're March or April or something like that. And we've got this horizontal line, which is your threshold. Development will occur if you're above that threshold. It will not occur when you're below that threshold. And here we've allowed the daily high to increase between 10 and 40%, the daily lows to decrease. So in this example, for all of these K scenarios, where we simulated it, we haven't changed the mean at all. We've just changed the daily temperature range. And the degree day model that is basically the area under the curve above the threshold. That's going to be what drives your temperature, your insect development forward. So this is an example of what happens for the number of simulated work for the number of generations for great berry moth under 81 scenarios. The scenario 0, 0, you've got your daytime things happening on your y-axis, your night times on your x-axis, and 0, 0 would be no change. But you can increase the high, you can decrease the high, you can increase the low, decrease the low. And the only thing I want you to note here is that daily temperature range will influence volcanism because of how it interacts with degree day accumulations. That's the take home message from that. Okay, so what I showed before was utilizing this agent-based or individual-based modeling, but it wasn't really a population model. I mean, we just had a fixed number of adults that we, well, in that case, we used overwintering pupae to initiate it, and just that was it. But here with brown marmoset stink bug, with a project that was led by Tracy, I think, we were able to go forward and add all these fitness parameters that I list on the left. Same sort of question. Here we're not moving forward in time. We're going to be just looking at how photo period and photo period and temperature interact to influence volcanism. And so now we have a population model which we can start with, say, 1,000 individuals, but the number of individuals is going to fluctuate dramatically depending on what's happening with these fitness parameters, which were all generated mostly by Ian Nielsen records. The top graph shows you in Bridgeton, New Jersey, shows one example. We did this for like, I think 10 or 15 different sites around the country over a 10-year time frame. Because this was all about what's going to happen with brown marmoset stink bug as it moves across the country. I'm pulling out an example from Bridgeton, New Jersey. The top just shows you a daily degree day accumulation, and the blue thing is the cumulative. And you can see that there were 2 years, 2010 and 2011, where relative to the baseline, if you will, I put an arbitrary baseline just on looking at this graph. Those were the 2 years that we had the outbreak years. Those are the 2 years that we had a tremendous amount of loss in tree fruit. And it didn't take that much more in degree days to cause that to happen. The other thing I want you to note is, if you look at the bottom part, we were able to simulate eggs, each nymphal instar, the adults, and we just grouped it here and taken nymph and adult. And you can see that the stage structure is shifting a little bit, and the relative population of the relative amount in each stage is shifting, and that's also going to be influenced by this. So we have these higher damage rates due to all those factors, and I just wanted to use this to emphasize that this is all influencing. It's called, I think of it as host plant interaction, species interaction. Ground murmurs think of how many, which life stage relative to what the crop was doing, that's the other species, what phenology stage was that crop in. So we're going to get shifts in those host plant interactions and species interactions. The other thing that happened, which was surprising, is it influenced which life stage overwinters. So this is an example from Geneva, New York. In 2005, you can start, this was, P was the parental generation or the overwintering generation. This is just looking at the adults. You get the parental generation, you get when the rise and fall of the adults from the offspring of that parental generation, the F1, and then the rise of the F2. And then at the end of the year, most of the population is in F2. But you look at 2007 or 2014, it's really clear in 2014, by the end of the year, it was about 50-50. So F1 population adults, which are not occurring till like early August, they're hitting photoperiod cues that are telling them to go into diapause, which is actually causing them to not survive as well because they got a longer time frame to finish off the fall and get through the winter. And as compared to the 2005, they're not hitting, you know, most of the population is in F2. Anyway, the interaction between development, temperature development, and diapause influenced who overwinters. And Eric Gottman, from his work, he's done a great bunch of studies. If you have populations that can overwinter in diapause as F1s, or I mean, I'm sorry, as univolting, maybe there'll be genetic requirements that this is a univolting population. They're going to go into obligate diapause. They're not responding to diapause cues. So we've got univolting European cornflower, but we also have what they call bivolting. And they coexist, and they're really not bivolting, they're multivolting. They're responding to diapause cues differently on a genetic level. And what Dr. Gottman is showing in his literature, I've only had a chance to interact with him a little bit, but he's clearly showing in his papers that we get selection for the multivolting populations. So we've got genetic selection happening because of this interaction with temperatures and photoperiod cues. Temperatures rising, daily temperature range changing, photoperiod's not changing, and the interaction is influencing lots of things with insect populations. And to summarize, those interactions are influencing the timing and abundance of each life stage and its post-plant interaction or crop damage or not. We're getting overlap of generations, overlap of life stages of insects more, and influencing which generation overwinters. Daily temperature range affects voltinism. We're getting increased voltinisms, and we're getting genetic selection for populations that have the capacity to increase generations. Okay, and finally, range shifts through migration. This is back to what I did with Union for Concerned Scientists. I just listed. Oh, sure, you know, here's a bunch of insects that really don't achieve good, strong pest status in at least central or northern Pennsylvania, unless we get significant amounts of migration. Now, that migration pattern might influence it. It's also the proximity of the source population, which I think several of the plant pathologists have referred to as well. So we've got, you know, this happening for a lot of our almost all of these are one family of insects, so not two a day. Diamondback moth is a different one. And it's also true for like cornleaf aphid and big leafhopper. Here's just some work that Lawton and all did where they pulled together historical trap catches from pheromone networks, that trapping networks, and looked at also soil temperatures and utilized some statistical tools to basically group these into patterns. And it identified, I think it worked pretty well, patterns of what corn earworm would do in its southern range, where it overwinters, high probability of overwintering. The transition zone, where some years you get some overwintering and some not, and the northern limits, where you're not going to get any overwintering. That's just a bit of a simplification. And then it's a better graph than we've had in the past, where we just use the 40-degree latitude as a cutoff. So that's your current status. But you take this forward through time using the RCP 8.5 example, and moving to number 2 here, B, the B example. Yeah, I think that's real. I've stopped telling growers that we don't have overwintering in Pennsylvania. To say we do, and we've got to shift the way we manage this insect. And you can see it moving forward through time. That's an example where an insect can overwinter to some degree relatively closely, and we're going to change our pest complex entirely. There's other cool ways. I was involved with a lot of aerobiology model that was supported with genetic tools for fall armyworm, and there we have source populations that are only occurring in the southern tip of Texas and the southern tip of Florida. And so we have some idea of their typical migration patterns, and some really good work just showed up in the literature, where they were able to look at corn earworm again, and the maps at the bottom, the red dot is an individual corn earworm, and then the color represents the probability of its source. And as you move into the yellows and greens, it's a higher probability that it came from that source. So we're starting to be able to actually look at where these insects originate from. And some more pictures of that. But for the migration questions, I would add, overwintering survival increases, influencing the proximity and abundance of these source populations. My question, I have no idea how this is going to play out in the world of climate change. Will airflow trajectories change? As part of these aerobiology models, you have the fraction of the population that moves into a very specific behavioral pattern that causes it to have a higher probability of being moved by airstreams. And so that the aerobiology models utilize that. We influence the probability of the population going into that migratory phase based on host plant relationships. So it's the degree to which the host plant, we're modeling the plant and the insect, the degree to which the host plant was stressed, and insects that developed in their larval stages under a stress scenario, we shot them up into the airstream with up to 90%. If they developed in a non-stress situation, usually it just was based on crop phenology, then we kept 90% local. We did not move very many up. But when you do move them up, so you've got these stress things influencing the probability of exhibiting migratory flight behaviors. And then you have the moving up through airstreams that, what are those patterns going to be? Another question I have no idea about, how do nighttime temperatures affect flight behavior? Because all those not too is we only move them up in the airstream at sunset, and we'll drop them down at sunrise and give them maybe 3 chances to fly it and have to land in suitable habitat, or else we die. So how does nighttime temperatures affect these behaviors? And then, yeah, there a lot of authors are suggesting that we are now they can start to document that you're getting return migration, or at least a fraction of the population that's coming back, and so you get these gene flow, resistance genes moving up, potential of those genes moving down and being selected for. So range shifts, interactions between phenology and volcanism, migration. I think climate change is going to influence all that, and that's all I have to say. Any questions?
Very good. Thanks, Shelby. I'm curious. So, you mentioned at the end about will the air biological trajectories change? Will the overwintering locations wind up changing, right? So that will undoubtedly change the patterns of those insects moving northward, flowing northward.
Yeah, we were using for the fall armyworm, we were using these high split, the same tools that you plant pathologists use as you move lists around. So we were actually using high split modeling for that particular night. But that was kind of based on historical patterns of jet streams, and well, they weren't way up in the jet streams, but yeah, I don't know if those are being affected by climates.
And then you plug in the ensemble models where you've got multiple trajectories coming from any given source, and it's complicated. Jim?
When you reach that conclusion about temperature selecting for more generations, is that generalizable, or was that specific to certain groups of?
I think it's generalizable. The example I was using was European cornmeal, but there are, diapause is a complicated process that's that has genetic variability to it. So we have some for the same species. So I'll use European corn borer, but I think this is relevant for other species as well. For European corn borer, there is there are two races, if you will, and one is obligate univoltine. So they're going to, they overwinter as pupae, if I remember right, but they'll emerge as adult. They'll go through a generation. When they become a pupae, they will always go into diapause. That's the univoltine population. But existing sympatrically are populations that their decision as to go into diapause depends on the photoperiod cue. And so they can get another generation and another and another and another. And at some point, some fraction of it becomes a suicidal generation, but some fraction of it will do fine. So you got these obligate univoltine, and you got these multivoltine populations existing sympatrically, and you've got selection happening for one versus the other, depending on, in part, by whether they were able to complete the generation versus what fraction of them just went suicidal. And that's, and so you're going to select for the multivoltine. That's what's happening with European corn borer as you get into warmer temperatures.
Do you think that will translate to?
I think it will translate to other insects that have obligate univoltine and multivoltine races coexisting. Yeah, I think so.
That's not
You get the relative fractions of those kinds of populations as you move from north down south change, because it's selected more for multivoltine populations as you're further south. So that's why I'm thinking it'll happen like that. Yeah, it's just a guess.